All right, the number 2002B question, we're going to start off with part A. A 1.5 gram sample of zinc is combined with some silver nitrate there, and they want to know what is the limiting reactant. So in order to do that, we got to get the two chemical amounts in moles first. So here are the mole amounts. We have this many moles of zinc and this many moles of silver nitrate. To determine the limiting reagent, we looked at the balanced equation. For every 1 mole of zinc, we are going to need 2 moles of silver ion. And since we have 0.0229 moles of zinc, that will correspond to twice that many, so I was about to say 44, but it's going to be more like 45 moles of silver, and you'll notice that this is how many moles we would need to consume that, and we only have 0.0275 moles of silver nitrate, so we do not have enough. And therefore, silver nitrate is the limiting reagent. Then in part 2 of A, they want to know, on the basis of the limiting reactant, determine the concentration of zinc after the reaction is complete. So since silver nitrate was our limiting reactant, we are going to start with 0.0275 moles of silver nitrate, or silver ion, and we are going to have a mole ratio of 2 moles of silver ion to 1 mole of zinc ion on the other side over here. And then we'll know the mole amount, and they want to determine the concentration, so we're going to have to take that mole amount and divide it by the liters. Alright, so I've calculated the number of moles of zinc, I've figured out the concentration, and this seems to be the answer. I'm going to go back and check sig fig since it's a numerical answer, and it looks to me like, obviously this all came from our silver number, and our silver number came from this sort of measurement up here. So I'm going to go back. It looks like it's 3 sig figs for the molarity and 3 sig figs for that, so I better add an extra 0 on here, and that should be the answer to part 2. In B, they want us to find the standard cell potential for the galvanic cell of this reaction up here, and on the year they did this, they did have a reduction potential table, so I'm going to write down the 2 reduction potentials that matter here. So here they are. You remember one of the 2 is going to have to be flipped over, and it looks to me like it's the silver one because it should be going from the ion to the metal, and right now, I forgot to write the ion charge. It's going the opposite way, so we're going to need to flip that one over, and then we're going to be adding positive 0.8 plus positive 0.76, and that should give us 1.56 volts. And check sig figs, we went 2 places beyond the decimal, 2 places beyond the decimal. So that's our answer to part B. In part C, determine the value of the standard free energy for the reaction between silver and copper. Well, we just found out the cell potential on the previous page, so we can relate the cell potential to the free energy by using Gumpy. And so the delta G is going to be equal to negative, we got to figure out the number of electrons. Well, and in part C we're doing a different reaction. So you notice that they have the cell potential right there. The number of electrons exchanged, well, if you look at the copper, it clearly was exchanging 2 electrons. And it was true of the silver as well. So I think N is going to be 2. F we know is 96,485. And the cell potential is going to be 0.46 in our new reaction. So when we calculate delta G, we should get negative 89,000 joules. And the sig figs are going to come down to the cell potential because this is a defined exact number, and so it should end up being 2. So that's the answer. Let's check and see if they said in kilojoules or joules. They didn't say either one, so this should be acceptable. Or you could write down negative 89 kilojoules per mole would be fine. And it is per mole for both of these. In D, you'll notice they're talking about a cell that is not at 1 molar, so it's at non-standard conditions. And that's a situation where you're going to be doing the Nernst equation to figure out the new cell potential. Now, I told you that in the new example, I think it's unlikely that they're going to actually ask you to do this, but we're going to do it here. Before we do that, though, let's make a little prediction, because I think it's much more likely in the new exam that they'll have us predict what's going on. You notice that the concentration of copper, well, it might seem that they're both going down, right? But that's probably not the best way to think about it. If they were similar concentrations, they'd probably have the same impact. But it looks to me like the copper has a much higher concentration than the silver. It's like we're increasing the concentration of the copper and decreasing the concentration of the silver. And so I think the reaction is going to shift backwards. So I wouldn't be surprised if we found a cell potential that was significantly lower than the 0.46. So it's a way for us to check our answer. Now let's go back to the Nernst equation. So we've got to decide which values go where. And remember that we're doing, this is the log of Q, it's products over reactants. So the copper ion is the product, and the silver ion is the reactant. Remembering to leave out solids. No solids go into this. And so we have our concentrations. This one on top is going to be 0.045 molar, and the one on bottom is going to be 0.010 molar. And N, let's see, we decided N, the previous one, was 2 electrons. And if we plug all that in, we should get a cell potential. Oh, by the way, I forgot to say this is 0.46 volts. If we plug all that in, our answer in the end is going to be 0.38 volts. So it did end up going down, and it's reasonable to have the 2 places beyond the digit because that probably reflects what we did before. And we also have 2 sig figs and everything else. And then lastly, E, under the conditions specified in part D, is the reaction spontaneous? Well, we can tell simply by looking at that cell potential that we had before. It was positive 0.38 in that previous part. And we remember that positive voltages mean that you're producing a significant amount of product in your reaction. So yes, the reaction is spontaneous. And I don't really have room here, but you would want to spell it out. And the reason, the rationale is because the cell potential is positive. It's as simple as that. I think you're done. You could talk about delta G if you wanted to, but I think that that's plenty of evidence.